talk is by Xujia.
So good afternoon, everyone. Thanks for the introduction. I would like to thank the organization committee for inviting me here to join this amazing event. And thank you all for attending my presentation here or online. My name is Xujia Zhu. I am currently a lecturer at CentraleSupélec, a university Paris-Saclay, and I'm affiliated to the Lab of Signals and Systems. Today, it is my pleasure to share some recent developments in surrogate modeling for stochastic simulators and some insight into this field. And of course, I would like to share some personal views of the current development. So in this presentation, I will first of all give a very brief introduction to stochastic simulators, and then I will review the existing methods, and I will then present two examples or two surrogate models that we developed within this project. And then I want to discuss some related research topics and some challenges in this field, and then conclude this talk. So just before starting the presentation, I would like to mention that the whole presentation will stay more or less at the high level, so I will not enter into the very detailed technical part, but I will mainly provide the main idea behind those approaches. So in engineering, simulators or computational models actually plays a central role. So what I mean about computational model, it is some computer code that takes some input parameters such as the geometry or the material properties and maps those parameters to a set of quantities of interest. In general, there are two types of simulators, deterministic or stochastic. So for deterministic simulator, it's actually a function of the input parameters, and that means a set of input parameters has a unique corresponding value of the model output. In contrast, stochastic simulators provide different results. We run twice with the same input. So if we run the stochastic simulator the first time, we get this value, and the second time we obtain a different value, so does the third time. So if we repeatedly evaluate the stochastic simulator many times, well, we could fit a distribution to the model, to the possible outcomes there. In other words, the output of a stochastic simulator is a realization of some underlying random variable. And the randomness comes from some latent variables that are relevant with the model output, but they are not explicitly taken into account as part of the input. So if we can only fix the input values, while the latent variables vary in their range of definition, the output remains random. And here we have two typical examples of deterministic and stochastic computational models. And this project was motivated by mainly some engineering applications. So here I will present three of them. So the first one is the seismic fragility analysis. So in this case study, the engineers are typically interested in the state of a structure given some macroscopic descriptors of an earthquake signal. And those descriptors are typically called intensity measure. They are, let's say, physically meaningful summarizing quantities of a detailed signal. So in this case, for a given set of those parameters, it will not give you a unique time series. So that is why, in the end, what we have is something called the fragility surface or fragility curve, which is nothing but the failure probability given those macroscopic values. A second example is from epidemiology, so it's an agent-based model. There, the individuals interact within the population, and for decision maker, they are interested in how some macroscopic measure could help contain the spread of infectious disease. And the third example is from a hybrid simulation, where we couple the physical simulation, like a real experiment, with a numerical model. So there's some coupling phase that transfers response from the physical experiment to the simulation part. And as there are real experiments involved, there are always some unspecified term that could affect the model output. So, due to the stochastic nature of stochastic simulators, in order to fully characterize the model output distribution, we need to repeatedly evaluate the simulator many, many times. This is called replications for the same input. In the context of optimization or uncertainty quantification, where we model those input parameters as random variables, we need to investigate this analysis for multi-value or different values of x to explore the input space. Both factors together result in a large number of model runs. So, but as you know, that realistic simulators can be quite time-consuming, which makes those analyses almost infeasible for complex models. So one common approach in engineering is to build a surrogate model or an emulator. Well, emulator is pretty simple. It's actually something behaves similarly as your original model, but much easier and simpler to evaluate. So basically, we could evaluate a surrogate model tens of thousands of times within a second with a standard laptop. So now let's have a look at like what have been proposed or what is actually ongoing on the development of surrogate modeling for stochastic simulators. So I clarified the existing method into 3 families. And of course, this is my personal choice, but then if you prefer some other ways to clarify them, I would like to discuss them with you after the presentation. And the first one, the so-called random field representation. So as the name indicates, this approach casts a stochastic simulator as a random field. So here, of course, for a given x, you have a random variable. But if we could somehow control the value of the latent variables, we have a deterministic function of the input parameters. This is called a trajectory in the context of random field. And the main idea of this approach is to somehow emulate the different trajectories, and from those trajectories to either use the empirical version or to reconstruct the random field. So how can we do this? Well, the first step is to control the value of the latent variables. So this is typically done through random seed control. And then we evaluate this trajectory on several points of the x, like experimental design. And then we apply some regression methods to emulate the trajectories. We do it for multiple trajectories. And then to extend to the continuous field, you can use Cohen-Loic expansion. But there you need additional step to estimate the distribution of the projected random variables. So here I will just give some, and this is the general idea, and I provide some detailed literature on this approach. And the second approach is a so-called replication-based approach. So here we leverage replications to extract some important information from the simulation. So for example, if you are interested in the 90% quantile, then for each value of the x, you run the simulator several times, and then you can estimate some empirical. You have some empirical estimates of the quantiles. Of course, this also provides you with some uncertainty of the estimate, and then you can incorporate those uncertainty into a regression framework and to extend those quantities to the whole field. And within this category, you will find most of the early work on surrogate modeling for stochastic simulators, especially the first one, the so-called stochastic kriging, where the authors were interested in the mean value, but of course they leverage replications to have a better estimate of the variance. And then I think this one is the most common one for US statisticians. Is in the regression setting. So more precisely, we have distributional regression. There, we typically have some assumptions of how the data are generated. They can be either parametric or non-parametric. And then we apply some estimation method, such as mean squared error. Those are based on the loss function, like the mean squared error, check function loss, also called pinball loss for quantile regression, or some strictly proper scoring rules for distribution estimation. And there, I think I don't need to enter into a thorough review of all the methods, but I would like just to mention some principles of them. So those methods are somehow sorted by their complexity or flexibility. So the easiest one would be to assume that the response distribution follows kind of a parametric distribution family, and it can be normal or exponential family as generalized linear model or generalized additive model would assume. Then we, instead of assuming a parametric family, we could assume that they are a kind of a nonlinear transform of some latent variables. And this would give you most of the state-of-the-art deep learning method, such as variational autoencoder, generative adversarial neural networks, normalizing flow, and diffusion model. And here, since we are interested in the conditional distribution, then the conditional versions of those methods are actually of interest. For example, for the diffusion model, then this is diffusion with guidance. Then, if we step further, we would have the most flexible family or type of method, which is the non-parametric models. So here you will find the kernel estimator, isotonic distributional regression, which is a very powerful non-parametric method if you have some prior knowledge of some stochastic dominance of the response distribution. And then we could have also the logistic Gaussian process, which is the Bayesian non-parametric density estimation. And this method has been fully investigated in the thesis of Untitled Chapter with Professor James Bourget in the audience. So a very short recap of these three types of approaches. So for the random field approach, well, it really produced the entire random field, which is very nice, but it requires certain regularity conditions of the trajectories and the seed control. And the second type of method just allows us to reuse all the existing regression like method as it is, but it requires replication. And this will typically a question like, how can we balance the trade-off between the number of replications and the number of points that different values of x we would put in the input space. And then the last one, the most common one, and it just allows us to run the simulator as it is. But then, in this case, we need to find a good balance between model flexibility and the sample size. So in our applications, we will typically within the regime of hundreds to a few thousand data points. So that is why we developed two stochastic surrogate models a bit dedicated to those engineering problems. Well, the first one is a so-called generalized lambda model, where we assume that, actually the parametric model, we assume that response distribution could be approximated by the generalized lambda distribution. So why do we have this choice? It is because this family of distributions is very flexible, and it can be used to represent most of the commonly used unimodel distributions, such as Gaussian, students T, and some extreme value distributions. And this is fully parametric. And a generalized lambda distribution is given by a definition on its quantile function by 4 parameters, lambda 1 to lambda 4. So lambda 1 is the location parameter, lambda 2 is the scale parameter, lambda 3 and lambda 4 are the shape parameters. So they control the shape of the distribution. And through this inverse transform of the quantile function, we are able to numerically evaluate the probability density function. And this slide summarizes, let's say, some important properties of the generalized lambda distribution. The figure on the left-hand side gives you all the possible shapes that could be represented by the generalized lambda distribution. And as you can see here, that it can represent some heavy tail distributions, which is very important if we are working with extreme load of the structures. And some moment up to a certain order, which of course depends on the value of lambda 3 and lambda 4, may not exist, meaning that this goes to infinity. And then under this setup, the distribution parameters lambda 1 and 2, lambda 4 are functions of our input. So instead of applying neural networks or using Gaussian processes, we propose using polynomial Chaos expansions to represent those 4 functions. So in short, polynomial Chaos expansion is a spectral method that it represents a deterministic function as a series of orthonormal polynomials. So here psi alpha are multivariate orthonormal polynomial basis functions that could be obtained by a product of univariate orthonormal polynomial basis functions. And here, those are the basis functions, and C1 and C4 are the model parameters to be estimated from data. And in practice, we would, of course, truncate those infinite sum to finite terms. So to construct a generalized lambda model, we need to find the basis function and also to then estimate the coefficient. Then how can we do this? Well, we assume that we are in a general regression setup. So we have a set of experimental design, and we don't have replications. And also we show that actually if we don't really treat specifically those applications, those replications, they may be less efficient in terms of the estimation. And the first step is to select the basis function for the surrogate. Well, here we apply the so-called feasible generalized least squares, which is a method that's largely used in econometrics to work with heteroscedastic data. So here we it's basically iteratively fit the mean and the variance from the residue. Okay? And then I call it modified because we use a sparse solver to select the basis. And the basis functions selected for the mean function are used for the location parameter lambda 1. And the basis functions selected for the variance are used to represent the scale parameter lambda 2. And for lambda 3 and lambda 4, they could either be fixed at a low degree, because in our applications, we observe that the shape of the distribution usually does not vary significantly too much with respect to the input. Or we could have some adaptive approach, like progressively increase the degree and then do some model selection with the information criteria. And then, of course, once we have the basis function, we apply the maximum likelihood estimation to estimate the coefficient. And for the theoretical part, we show the consistency of the maximum likelihood estimate. So this is the first approach we propose to work with more extreme load and unimodal distributions. Then it comes to the question that what if the distribution is multimodal or it can be more complex? So instead of resorting to a mixture distribution, here we propose something closer to a latent variable model. So here we introduce an artificial latent variable to formulate the polynomial Chaos expansion together with input parameters x. And then we add an additional noise to regularize the distribution, because otherwise this is a polynomial, then the resulting distribution are usually irregular. So this is why we add this additional noise to regularize it. And from this formula, we could write the density function, which involves this one-dimensional integration. And a very nice property of using polynomial Chaos expansion is that some important quantities could be computed analytically by simply post-processing the surrogate model. So for example, if you want to do Sobel indices or Sobel sensitivity analysis, you do not need to run an additional Monte Carlo simulation of the surrogate, but you could read directly the Sobel indices by post-processing the coefficients. And of course, for the estimation, we have two parameters, or two sets of parameters to estimate. One is the coefficient of the expansion. The other one is the standard deviation of the noise. So for the coefficient, again, we use maximum likelihood estimation. And here it involves this one-dimensional integral, and we used a one-dimensional quadrature because it's a one-dimensional integration. It's not too hard to perform some numerical integration computation. And for the standard deviation there, we observe that the likelihood could be unbounded if it is equal to 0, and this makes the whole optimization problem, especially in terms of the theoretical consistency of the likelihood, maximum likelihood estimation ill-post. So that is why we treat those parameters as hyperparameters and use cross-validation to tune its value. And we also use a cross-validation score to find a suitable distribution for the latent variable, usually between uniform and standard normal distribution, and also to find a good truncation scheme, basically how we're going to formulate our expansion. So now let's have a look at some numerical examples. I show the predictive distribution at different locations of the stochastic simulator. And the first example is the stochastic SIR model. SIR stands for susceptible, infected, recovered. So this is the agent-based model that you would use in epidemiology. And the response distribution, since we don't know its form, we use replications to have a reference histogram. And we observe that it is unimodel, and the stochastic polynomial Cal expansion, SPC, and the generalized lambda model both represent quite nicely this variation of the shape, because I don't have the same scale of the distribution, but actually here you can see that the span or spread of it is around from 200 to 600, and here this one is just from 50 to 250. And then if we have bimodal distributions, of course, then the generalized lambda model will not work, but the stochastic polynomial Cal expansion still somehow captures the variation of the underlying distribution. And for more quantitative comparison, we propose the normalized Wasserstein distance. So here we measure the Wasserstein distance between two probability measures. One is the reference, the other one is the surrogate. And then we average those distance among the values of x, and then normalize it by the variance of y, which gives something similar to the normalized mean squared error. And this is the convergence curve that from the previous two case studies or examples, easy examples. And we observe that when the model or when the underlying distribution is unimodel, then the two proposed methods actually produce quite correct results. But if we have bimodal distributions, then the generalized lambda model actually gets stuck at some point, and the stochastic polynomial Cal expansion still provides quite accurate approximation to the distribution. And of course, those are very simple examples, and then we apply the proposed method on the application that I mentioned before. So the first one is the seismic fragility analysis. The diamond points represent the reference failure probability coming from the replications. And the fragility surface is the one that we obtain from stochastic polynomial Cal expansion. And the second example, where we apply the generalized lambda model to emulate the extreme load of wind turbine application. So this is basically the flip-wise bending moment at the root of the blade of a wind turbine. And here you see that it's predicted quite well than the quantiles of the response distribution. And then we have also leveraged those surrogate models to perform sensitivity analysis of stochastic simulators. So we extend the framework usually well-defined for deterministic simulators to a stochastic setup. And this is the result of the hybrid simulation example that I mentioned at the very beginning. So that's pretty much it. That we defined some methods, and then they tend to work well in our applications. But then I would like to discuss a few, let's say, challenges or related research topics in this field. So the first one is how can we actually evaluate the model accuracy? Because so far in my previous example, I do need some reference distribution. Okay, but this one, of course, we need to replicate. We do have the budget, we could replicate the simulation, but then the question is where to replicate and how can we validate the model with the minimum efforts of computations. And then scoring rules actually provide quite sound and practical alternatives. I think there will be a talk on scoring rules probably tomorrow. But then it's usually used to compare probabilistic forecast. But how can we, let's say, easily explain those scores if we, for example, calculate some leave one out or negative log likelihood, this score, and it is hard to communicate to the engineers. And the second question is the measuring of the uncertainties. Of course, we could use the full Bayesian setup. I think there is some work on using Gaussian processes to represent those parameters instead of using polynomial expansions. But then we could have the bootstrap approach. But then there usually the common question that we would ask is, does the bootstrap consistency hold for the models that I developed before? And then we have the conformal prediction. It's a very popular method nowadays in machine learning and UQ community. We have tried to somehow integrate those methods, but then we observe like when we have very limited data, we tend to use full conformal prediction, but then that one would take a lot of time. And it has always this question of local validity of the coverage. I think I'm running out of time. I'll quickly sum up everything. So here, another aspect is the sequential design of experiments. So one is the current approach are mainly focused on using Gaussian processes to optimize the mean function. There are some ongoing work to extend it to, let's say, quantiles and expectiles, like in the sequential design of experiments, but more for complex quantities such as values at risk, like super quantiles, then it's still an open question. And then for engineers, we're also interested in the reliability analysis. So I attended a PhD defense on this topic last week, and I got to learn that the current approach are mainly based on some local uncertainty measures. But then how can we integrate this framework into the stepwise uncertainty reduction framework is also like we are currently investigating it. And of course, there are more bunch of questions, so I will not steal more time of the next speaker. I'd like to thank you for your attention, and I look forward to your question.
Do you have any questions? Just before ringing the bell, I told David, like, oh, we have such an active audience with the questions, and I think I jinxed it somehow.
It's because of lunch.
I know, but still. So no questions? I do. Yes. Oh, great.
With the conditional dependence and Sobol indices, I've seen it amplify things like populars, things like that. Would it be the same for the stochastic polynomial?
Exactly. So here, you mean in the case if we have multiple output there?
Multiple outputs.
Exactly. So here we could either resort, let's say, deep learning models, because if we have many dimensions, then probably it is hard to really model the conditional dependence through a common method. But then here we are again in the relatively small data regime, so we need to apply some more, let's say, like transfer learning or meta-learning method to make maximum use of the data, of the available similar data, to work with complex models. Otherwise, if you have like only one or two, or a few more output, yes, indeed, I think the copular one will be the first guess I would think in mind. But then, of course, if you model it through a copula, then it's parameterized. And then how can you represent those parameters? You can either use these polynomial expansions or resort to Gaussian process if you want to have some uncertainty, like quantification of the estimate.
Any other questions? I do have a question. So you presented like the 3 families of approaches which exist, and then moved on to presented your own stochastic simulators.
Yeah.
Probably I missed it, and it's a very naive question, but what kind of drawbacks were you trying to typically solve by proposing new ones? I mean, I've understood that you can capture like more general form of distributions, but is there something that was like not solved at all by any of these models, or like what was the motivation?
Well, the motivation was basically those applications from engineering problems, and we observed that most of the problems we have are, at the very beginning, we observed that they are usually unimodal. So that is why, to somehow bypass the normal assumption, well, of course, we could try the any other parametric families, but here we want also to have some flexibility in the modeling part. So that is why we developed the first approach, this stochastic, this generalized lambda model, because this is everything's parametric, and you could also have some adaptivity in the polynomials. So like here, I did not implement the regularized likelihood or penalized likelihood estimator, but the problem here is that the likelihood is relatively difficult to optimize. That is why I did not really try that one, but instead I used the physical generalized least squares to find the basis function for the location and the scale. And I agree with you that there are many existing methods, and we actually started from this one, from the replication-based one, and then we find that this, I mean, if you don't really treat the replications in a very specific way, they don't really give you a very good estimate of the distribution. So that is why somehow we think we need to leverage all the available data for the estimation. That is why we switched to this one.
Okay. Thanks. No more questions. Okay, so I think we can thank again the